Pure hydrocarbons, the chemical foundation of fossil fuels, are incredibly stubborn. Their atomic structures are perfectly balanced and tightly bound, causing them to resist reacting with most other substances. In their raw form, these molecules are a chemical dead end. To alter these inert structures, chemists must create a point of vulnerability. They do this by introducing an aggressive chemical infiltrator, a halogen, such as chlorine or bromine. Removing a hydrogen atom from a hydrocarbon and snapping a halogen into the vacancy creates a haloalkane. This connection is a polar covalent bond. Electronegative halogens pull the shared electron cloud, creating a permanent electrical imbalance, a partial negative halogen and a partial positive carbon. This internal electrical tension transforms the molecule. By establishing this specific polar weak point, chemists turn a previously unreactive hydrocarbon into a viable starting point for complex synthesis. Inserting that halogen requires precise control, but the earliest methods were blunt. Free radical halogenation involves saturating alkanes with halogens and blasting the mixture with intense ultraviolet light. The problem is that the reaction is indiscriminate. Once the UV light breaks the halogen bonds, they don't stop after replacing one hydrogen. They relentlessly attack the molecule, replacing multiple hydrogens in a chaotic chain reaction. This produces a mixture of different compounds that are nearly impossible to separate into pure substances. For a chemist who needs a specific, isolated molecule, this method is too unpredictable for precise work. To gain better control, chemists often use an alternative, adding a hydrogen halide across a carbon-to-carbon double bond. When this double bond splits to accept new atoms, the placement is governed by a physical law known as Markovnikov's rule. The rule dictates that the incoming hydrogen atom will attach to the carbon that already has the highest number of hydrogens. This leaves the adjacent carbon open for the halogen, resulting in a predictable, stable molecular structure. Successful synthesis relies on exploiting these inherent physical biases. By following the molecule's internal logic, chemists can place a halogen at a specific coordinate, rather than relying on brute force. Another pathway to avoid the chaos of alkanes is to start with alcohols. But because alcohols behave differently depending on their structure, chemists must first determine if the molecule is a primary, secondary, or tertiary degree. The diagnostic solution is the Lucas reagent test. By mixing the alcohol with zinc chloride and hydrochloric acid, the specific time it takes for the liquid to react reveals the degree of the alcohol. Tertiary alcohols react instantly, turning the liquid opaque. Secondary alcohols take roughly 5 to 10 minutes to show any change, while primary alcohols stay perfectly clear at room temperature. Once the alcohol is identified, it can be converted using what is widely considered the most efficient reaction for this purpose, thionyl chloride. When thionyl chloride reacts with the alcohol, the unwanted byproducts, sulfur dioxide and hydrogen chloride, are naturally produced as gases. Because these byproducts simply bubble out of the solution and escape into the air, the reaction requires no extra purification steps. It is a self-refining process that leaves behind a pure, high-yield haloalkane. Even with these established rules, the periodic table presents a specific anomaly when dealing with the smallest of the halogens. Generally, as you move down the halogen group from fluorine to iodine, the atoms get larger and the bonds to carbon get longer and weaker. This chart shows the dipole moment, or the measure of electrical imbalance in the bond. The trend should decrease as atoms get larger, but fluorine shows a lower dipole moment than chlorine. This occurs because fluorine is uniquely compact. Despite its immense electrical charge, the physical distance between nuclei is so short it reduces the overall dipole value. These atomic measurements are more than just data points. They define the reactivity that makes the haloalkanes so valuable to global industry. Because the carbon-halogen bond is polar and relatively easy to break, it acts as a universal mounting point. Chemists can swap the halogen for a hydroxyl group to create alcohols, or nitrogen to form amines. This single substitution pathway provides the foundation for modern manufacturing, from the synthesis of PVC plastics for infrastructure to the creation of the complex molecular rings found in anti-inflammatory drugs and antibiotics. By mastering the controlled disruption of this one bond, humanity gains the ability to assemble the materials that define the modern age.